I thank Adam for a wonderful setup for what I'm going to be talking about at this point, which is optimizing storage and memory hierarchies, largely focusing on CXL. My name is Andy Banta. My official title is the storage janitor, and I work at Magnition right now, among other places. There we are. Amazing. So one of the problems that we run into now with modern storage and memory systems are that we've built a huge hierarchy that has lots of different steps, lots of different tiers in it, anywhere from register-based memory all the way out to optical-based drives, that type of thing. And figuring out how to configure this appropriately, figuring out data placement, figuring out how to size the various different tiers, figuring out what interconnects to use can be a larger task than an engineer or a team of engineers can figure out. SNIA has been driving an awful lot of these changes and adding an awful lot of the different pieces that end up in here, making this problem worse. Most people don't really know what Magnition is, so let me just give you a quick overview. Magnition has built a framework for simulating various different tiers of memory and has come up with algorithms for figuring out data placement and sizing and interconnects. We can do this in the simulations. We can also do this real time. For those who aren't familiar, Magnition has a handful of patents and some award-winning papers out on the subject of doing data placement and sizing. So right now, the engineering world has a bunch of different disciplines in it, like we have electrical engineering, chemical engineering, mechanical engineering, civil engineering, bioengineering. All these different things use simulations to come up with answers to their solutions. Why can't software engineering and system engineering, system design engineering, use the same approach? You do this because it's cheaper, it's far less expensive than trying to figure it out from scratch. You can come up with a lot more flexible possibilities than you can building out hardware. As Adam was talking about, there aren't CXL devices out there that you can necessarily test on right now, but if you simulate them, you can do them. An aspect that one step beyond what Adam was talking about was that you can't necessarily test at scale, even if you can get a few of the devices. You can't necessarily build out at scale systems that you want to try. So it makes sense that we should start using simulations in software design and in system design rather than just in physical design practices. I mean, the values are huge. It's faster to prototype, it's cheaper, it's a lot easier. You can come up with a lot different configurations, and it's the same practices that should apply to any other of the engineering disciplines that are out there. This is just showing a simulation, a stepwise approach to solving a problem and coming up with a better answer through running simulations rather than trying to build it out on your own. One of the cool things about simulations is it tells you things that aren't going to be intuitively obvious otherwise. So this is a genuine graph that we got from one of our simulations where we're comparing latency and cache size in a particular configuration. And you can see that there's this huge knee in the center of it where even if you expand your cache size out 8 times, you haven't really improved your performance at all. This curve is invisible until you actually go through and do the simulations to find it. You can't just intuitively say this curve is going to exist. That is why the simulations come in handy for this type of thing. So let's talk a little bit about how we go about this. Magnition has put together a framework that will build out deterministic behavioral simulations by using different pieces, potentially like the pieces that Adam was talking about in the previous talk. Piece them together as you want. Magnition has a library of components that are out there already. We can also draw on public source or open source systems that are out there. And typically we would work with companies who were interested in designing their own proprietary pieces to fit into these simulations. When you build out these simulations, you can go in and say, here are the things that I want to vary to try out the various different simulations. You can also plug and replace components to try out different things. And while you can run these against benchmarks or synthetic data, we also have the ability to play back actual traces, so you can try these against genuine applications, genuine workloads that you would be interested in running. So the whole idea here is that we build a framework. We're working with a little company in Berkeley named Liquifraca to do this framework. As I mentioned, we have a handful of components that are out there already. We have like an SSD simulator and a DRAM simulator, an HTTP simulator. They're various different things. One of the easiest examples to show how we would put these simulations together is using something like a cache simulation. So we kind of look at a cache as a decision point on whether there's something that's stored in the cache or whether it's not stored in the cache. So we have an input, and in this diagram, we're just going to say that a hit goes down and a miss goes off to the side. With the cache, you have various different media types. So typically, this would be a fast media type, and this would be a somewhat slower media type. And what we do is that we simulate those various different types of media. So it could be an SSD or DRAM or whatever. We also have this idea that there's interconnects from the input to the cache and from the cache to each one of the media. So we just call these wire components. And we can build this out to be a multi-layer cache if we want. We can build, this is a fixed diagram. Jay asked this question when I first presented this. It's like, is this all you do? And it's like, no, these can multiplex, these can fan out, these can be, the components can fit into any type of framework that you want. This is just an example to explain how this works. So when we get into the media component, see, I fixed this in my slides, but it's still here. So the media's components can be memory, disk, cloud storage, network storage, whatever you want. We have a handful of ones that are out there. MQSim is a SSD simulator that's out there that we've adapted to work with our simulation. There's also various different DRAM simulators where we can simulate contention and whatnot. So the idea that there's going to be parallel access or contention or queuing on any one of these devices is simulated as well. And one of the nice things about the simulation is these media devices don't actually need to store anything. All we need to do is say whether the data that we're interested in is there or not, and all we need to do is simulate the delay in getting the response back, because we don't really care what the response is. We just want to know the delay in getting the response back. So in this case, we could have something like DRAM here and an SSD here and a network storage box or cloud storage in this example. Similarly, the wire components would be memory buses, Ethernet, disk adapters, whatever would be something that would interconnect these various different devices. They can even be something that would transform a request, like in this case, we could have something that would be coming in as an HTTP request that would get translated into an Ethernet request. They work for a variety of different memory buses. We can calculate hops and topologies if there's various different lengths of things here. And again, all we have to do is introduce the delay associated with it. We don't need to actually do any of the the real work that would be happening here. So the simulations can work far faster than they would in real time. So in this case, we could have something like a URL here, and we could have RAM bus or DDR to connect our DRAM, or potentially even CXL, something like a PCIe bus between the two different caches, and NVMe here, and something like iSCSI or S3 to go out to our final storage. In addition to this kind of layout, a cache itself has a handful of different components in it. So we can go in and we can change the algorithms that we play around with in a cache. So we can change the allocation, the lookup, and the eviction algorithms in a cache, for example. And we've actually found, one of the examples I'll talk about in a few minutes, we've actually found that just changing the algorithms in the cache has far more effect than changing the size or the type of media that the cache talks to. What I mentioned earlier, while you can run synthetic workloads, we are much more interested in doing playbacks of actual workload traces. So you're getting information on the workload that you're interested in, not just saying what a benchmark would say. So some of the traces that we've looked at so far would be content delivery networks. If you're trying to put together an AI system, you could do like a learning or inference workload. If we were trying to put together a storage array, you could use something like a storage trace as your workload. And for HPC systems, you could use something like electronic design automation or gene splicing or whatever to be your workload as well. And we have a variety of different ways currently that we can read in playbacks. We can use the vSCSI trace from VMware. So this would just be all the virtual SCSI commands that come into a virtual disk on a SCSI device. We can use like an Ethernet trace that you would get from Wireshark. We can use an HTTP trace that would be potentially a dump from an HTTP server. We can use something like memtrace that would actually be reading all of the tracing all of the reads and writes into a stack of memory. So let's talk about some of the different ways that we would potentially be using these simulations. So these are just general purpose cases. The idea that you have a fixed cost bill of material. So you're trying to build out a system and you know how much it's going to cost. You can run a simulation against this and say, okay, here's how I optimize this cost into a list of bill of materials for the application that I'm trying to build for. Another example is you already have some infrastructure, or you already have a data center, and you're trying to repurpose it. What's the best way to configure that data center for the workloads that you're trying to do? There's also the idea that you're trying to get rid of wasted resources. You've built out a system, or you're trying to build out a system. If you go out and start trying to constrain the resources to see which ones really don't make any difference on your outcome, it's a way of discovering wasted resources. You can try to come up with the best performance for a given workload. Most commonly, people will try to come up with what is the best performance for a variety of different workloads. So I have all these different things that need to run together. What is the optimum setup to do this? And while these graphs that I've shown you have tens of points in them, what we actually do with our simulators are run millions of experiments and end up with graphs that give you millions of data points. So you can try to start finding trends in that. So it's not just a small sampling. We run typically millions of samples against our simulations to come up with the best answers. And because we're running this many simulations, it means that you can vary quite a few of the you can vary quite a few of the decision points or components or other pieces that you can vary in your system. So some specific use cases would be something like a CXL system. I did a talk at SDC in December that spent the entire talk was spent talking about CXL use cases. Just to bring this out in particular, following on with what Adam was saying, once again, thank you for that great lead up. This configuration, if we were talking about type 3 CXL, would have potentially 7 different NUMA nodes with anywhere from tens of nanoseconds of delay to hundreds of milliseconds of delay. And the only way that you can actually figure out the best way to use that is to run some simulations on the applications you want to use on it and figure out how to spread them across your various different NUMA nodes. Another example that we've run into is the idea that somebody is trying to build out a hyperscaler or a large-scale HPC system to do simulations, and they're going to have a variety of GPUs and CPUs and Ethernet interconnects and HBM interconnects and potentially CXL memory hung off of your CPUs. What is the appropriate way to build this type of system out to be able to make the best use of it for the workload that you're trying to do? And this might not be the same if you were trying to do like design automation versus whether you're trying to do AI learning. So you would want to run the specific workload that you're trying to learn to figure out what the exact specific example is. And again, I know this is way too small to read, and in my slides, I had nice big highlight arrows pointing out what the various different pieces are, but this is a content delivery network example. Here would be the web traffic that's coming in. This would be one of many regional points of presence, and this would be somewhere where the source material is. So the point of presence is this big box here, and the point of presence has a handful of servers in it, and each server has DRAM in green and SSD in blue, in case you can't read the text that's there. As I said, I had nice big red arrows on it to point out what they were previously, and I don't have those anymore, so I'll just have to do this and this and this and this to point it out to you. This is the most recent experiment that we worked on with. It was done as a research experiment in conjunction with a handful of content delivery providers that are out there. And we tried doing various different things like varying the number of servers or getting rid of the number of servers that had DRAM as the cache and only had some that had SSD in them, or varying the size of the SSD and DRAM. One of the things that I really didn't show in this example is one of the most important changes we made was to vary the cache algorithms. And varying the cache algorithms had more effect than doing any of this. And just so you know, one of the key things that you want to do in a content delivery system is be able to get a cache hit within these pops without having to go to the origin. Anybody who's tried to look up a 3 or 4 year old SDC video from YouTube, it takes numerous seconds, tens of seconds for it to actually get to you, which is why that you would want something like that cached. The final thing that we really want to focus on is the ability to get understandable results. And typically these simulations dump stuff into a huge database, and you need somebody to figure out how to pick through that database and figure out what it means. What we've done is we've assembled a notebook of graphics libraries where you can say, for this experiment, I want to look at it in this way. And this is some of the actual results from our content delivery network. And you can see that there's about a factor of 3 difference between when we run a fixed topology and when we run a variable topology. This is just one of the easy examples of finding out what we want to find out, showing it graphically. We have a huge variety of different graphs that we can print out or we display. We have heat maps. I didn't want to get into a whole lot of examples of what we have. What I did want to point out is this simulation has proven results. We worked with a major storage company, and before they started working with us, they were running a couple experiments a day. After they started working with us, we were able to simulate about 50,000 experiments a day. And over the several month engagement we had with them, they ran more than 1 million examples. And anybody who's ever worked with storage technology knows that getting double-digit performance increases in your cache is huge. And in some cases, we were getting almost a 50% improvement. So this is a real-world result with Magnition working with a storage partner who won't allow us to use them as a reference. One of the 2 major storage companies in the world, if that narrows it down for you. So again, this is just a quick overview of the various different pieces that Magnition has, and on my slides, I actually added my contact information here. But you can reach me at andy.banta@magnition.io. I am on Twitter, if anybody still uses that, at @andybanta. I am on LinkedIn. Feel free to contact me anytime. And I appreciate your time. Questions?
Very nice, thanks. We actually funded some work at Georgia Tech. It's called Spatter. And so what we do is we take pin tools and get memory, address offsets and links that we read or wrote across thousands of machines doing these complex simulations. So we simulate too.
Okay.
For the reason that we can't test what we do. And you can just think about what that means. But we also are generating a ton of memory traces and making them available because memory traces aren't classified, but applications are. So we are hoping that there'll be lots of sites that generate these traces, and then Spatter will replay them. So if you ever want to replay them against a simulated system, there's a replayer out there that will replay it. So we play in this game a lot. HPC plays in this game a lot, as you said. And there's a source of lots of data that are memory traces.
Okay, excellent. You're familiar with the IO Traces technical working group in SNIA?
I am, but I don't think that does memory, does it? It just does IO.
I am not sure. I know that they are very interested in IO traces, and they keep asking Magnition for us to share some of the IO traces that proprietary companies have shared with us, with the caveat that we use them only to use in our own simulation. And it's like, no, we can't give those to you based on the agreement we made.
Right.
But
if they want memory traces, I can generate those like the wind.
Well, absolutely. I mean, memory traces are awesome examples of things to do, and I think especially apply to it. Even though this is the Storage Developer Conference, it seems to be the idea seems to be that memory is becoming the new storage.
Thanks for the talk. And the thing I would be most interested in from your analysis, you're mentioning CXL from tens of nanoseconds to milliseconds. If you could publish classes of applications and roughly how much latency they can tolerate, that would be pretty big, I think, for adoption, right? And give people kind of targets to look at and real expectations of what could happen in a faster manner, right? So I'd be very interested in kind of that output.
And I agree entirely. I think this ties in very nicely to an awful lot of the work that the SDC group here is doing as well, because I think one of the things that's going to fall out of doing that type of analysis is, okay, we know where we need to move the memory, how do we move it? And I think that what they were working on is a big part of that.
So we have instrumentation that will tag the pieces of the memory trace so that we know what parts of the codes are generating those things. That might work really well for what you're talking about, Adam, where applications are big and complex, and so knowing what part of the memory you could put into CXL versus what parts you can't, and what that implies to your application seems to be super important. So there's kind of a path to get there. Wonder if we could promote it somehow. Anyway.
Absolutely. Well, thank you for the information.
Yeah, I think that there are two papers, one from Microsoft and one from Google, that kind of goes into that on classes of applications that are latency sensitive or not. One of those papers from Microsoft, they assume a static memory, so there is no promotion, demotion, they just ping certain parts of the code on fast memory or far memory. So that really helps. And back to how do you have a simulation for that? Like if I can get memory addresses and part of the code, can I plug in and understand what parts of my code could be hosted on far memory or not?
The answer right now is no. We have the framework,
Okay.
and we certainly see the application of how it would work with CXL. We have not pursued anything other than just making sure the framework understands that CXL could be one of the workloads and how to piece it in there. As I said, the most recent work that we've been doing has been on content delivery networks, but the simulation framework is certainly capable of handling anything that can be broken down into components.
Yeah, in this case, I also work on, but with latency comes the bandwidth on the storage, where there's a point where the cache becomes a bottleneck for bandwidth.
Absolutely, yes.
Right, so
And,
you could just, be better off just not having cache in the multiple devices.
and that's entirely a possible situation, and that would be one of the things that we could definitely simulate.
Yeah, when you mentioned the MQSIM, is that a proprietary software?
No,
or-
it's a university put together open source project that we've just adapted to work with our setup. It's nice because it's one of the cool ones that has done a really good job of figuring out contention, and it actually works like you would think an SSD would, and it also takes into account that once you've entirely written the SSD, the characteristics change as you start doing garbage collection on that.
Sure, yeah. All right, thank you.
Uh-huh.
All right. Thank you, Andy. Let's thank
Quiet,
Andy.
Jay. Thanks. Thank you.